On behalf of 24HourAnswers.com, I welcome you to today's lesson.
In this video, we're going to look at two examples of finding the derivative function. This is going to be the long way, the first way that you will see how to find the derivative in your Calculus 1 course. There will be much shorter and faster ways of doing this in the future. So you have, depending on what textbook you're using, more than likely you're going to see one of these two here, and the only difference between them is the notation. Here we have a h in our limit, here we have a delta x. But as you can see, wherever we have a h up here in this little function thing, we have a delta x down here in this one. Means the same thing. I'm going to stick with this one here, but again, h is the same thing as delta x. As you can see, all these h's here have these delta x's down here. Sometimes you will see derivative notation as f prime of x. We call that prime. dy dx means the same thing. Also a y prime. These two right here, actually these three are the most common ones that you'll probably see in your text or in your course. So we have two examples. Let's start with number one. So we have a linear function f of x equals 2x minus 1, and we want to find f prime of x. This is the definition of a derivative, the formal definition, and what we're really doing here is we're going to find a limit. We're going to let h approach 0, and as you can see, we have a problem right there because we can't plug 0 into our denominator. We have function notation up here, and really what we want to find here is this. We want the limit as h approaches 0, and f of x plus h simply means take x plus h and plug it into the function. So f of x plus h will look a little something like this. 2 times x plus h. What I'm doing there is I'm taking that x plus h and I'm plugging it into that x spot. Now let's not forget to subtract 1 because this right here is f of x plus h. Again, I took the original f of x function, I took the x plus h, and I plugged it into that x spot. Then we got to remember to subtract 1. Now we need to subtract with that f of x. Well, f of x is exactly the original function that we have. I'm going to put that in parentheses because we are subtracting this, so we have to be careful with our signs. And now we divide all this by h. So looking at this one more time before we evaluate this, f of x plus h is this stuff right here. It's this exact function, except wherever we have an x, we plug a x plus h into it. Then we have our subtraction, and we are subtracting f of x, which is just the original function itself. Nothing's changed about that right there. So what comes next is hopefully somehow or another we can get rid of this h at the bottom. Since we want to plug 0 into h, hopefully we can get rid of it. So we have the limit as h approaches 0. Let's distribute 2x plus 2h. Don't forget your minus 1. Minus 2x, don't forget to distribute your negative here. And then this becomes a plus 1 right here when you take a negative times a negative 1. This is all over h, and let's see what happens. So now the limit as h approaches 0, the 2x's cancel out, the negative 1 plus 1 cancels out, so we have 2h over h. We can cancel the h's out now, and therefore we have our limit is 2, and this is actually our derivative. What you're going to learn very soon, when you have a linear function, 2x minus 1, the derivative of any linear function is going to be the slope of that line, whatever line it may be. And notice this is a y equals mx plus b. The derivative of a linear function is always going to be the slope of that linear function. As you can see here, we got a limit of 2, which is our derivative, and as you can see there, a shortcut actually is that the slope of our line is going to be the derivative function. More on that later, but if you did check out the real-world introduction to the derivative where we said the derivative is the slope of a tangent line, the only way we can create a tangent line to a line is to pretty much have the same line itself. And in that case, if we're talking about the same lines, we got to have the same slopes. Our second example, a quadratic. Don't let the notation here confuse you. Y is the same thing as f of x, and we want to find y prime, so we can still use this stuff right here, even though it doesn't say y prime equals blah, blah, blah. Really what we're going to do is we're going to still find a limit as h approaches 0. And in the first example, I took that x plus h and I plugged it into the x's back in this linear example, but we only had one x to plug that x plus h into, which is what we did right here. you want to make sure you plug x plus h into all of the x spots in the function. So we have to do it in 2 spots right here. So it looks something like this, 3, and we got x squared. So we want to plug x plus h into that spot. Don't forget to square it. 3x squared minus 5x, so we subtract 5 times x plus h plus 4. And this part that we have here is our f of x plus h. We've taken the x plus h and we've plugged it into every spot where we had an x. Now let's subtract the original function, or in this case let's subtract the y function, but it's still subtracting this entire thing. So again, be very careful, we are subtracting the entire function, so let's wrap it in parentheses, or if you'd like you can go ahead and change the signs of those right now. Either way will work just fine, and this is all over h. So there's quite a bit of algebra to do in this example. We need to make sure we take x plus h and square it. Let's make sure we distribute this -5 to this, and then let's make sure, if you have not already done so, change the signs of all of these. And again, our ultimate goal is to hopefully be able to plug 0 into this thing. For right now, we cannot because of our 0 in the denominator. So limit h approaches 0. We have our 3. And now x plus h squared, be careful with this. X plus h squared means x plus h times x plus h. Doing a little bit of FOIL method, x squared plus 2hx plus h squared. Make sure you FOIL that out or multiply your 2 binomials correctly together there. Distribute the -5 to both of these terms. So minus 5x minus 5h. Don't forget your plus 4. And now distribute your negative across here. So minus 3x squared plus 5x minus 4. And this is all over h. So all I'm going to do here to save a little bit of space is distribute this 3. So 3x squared plus 6hx plus 3h squared. I distributed the 3 to all 3 of these terms. So replacing that, and now let's see what happens. Again, we're trying to get rid of this h at the bottom, and that's your main goal every time you find these derivative functions using what I call the long technique. So the 3x squareds, they cancel out because we have a positive and a negative. We have a -5x plus 5x. We have a plus 4 minus 4, and I think everything that we have left cannot be combined or simplified. So we now have the limit h approaches 0, and notice these terms that we have left. We have a 6hx, a 3h squared, and a minus 5h. That's all we have left in our numerator. So what we're going to do with these pieces is we can factor a h out of all of them, since every single one of these terms that we have left all have at least an h in it. So factoring that h out, we still have 6x left in this term, plus 3h, and again notice there we had a h squared, so all I'm doing is pulling 1 out. That's our common factor, and then we have an h that's getting pulled out of that, so we're left with minus 5, and this is all over h. Now we can get rid of that denominator that's causing issues. That's your main goal every time. And now let's evaluate this new limit. We have the limit as h approaches 0 of 6x plus 3h minus 5, and if you plug 0 into this now, which is totally fine, 3 times 0, it knocks out this term, this 3h, so we are left with 6x minus 5. This is our limit as h approaches 0, but it also turns out we want to find y prime. Well, y prime is going to be that 6x minus 5. This is our derivative function. This is the slope of a tangent line in relationship to this particular quadratic. Later on down the road, probably if you're in Calculus 1 right now, if you're learning about this stuff right now, within the next, I don't know, maybe month max, maybe a few weeks, you will be able to look at this, not do any of this stuff, and you'll be able to find this derivative here very fast. Trust me. But for now, if you're going through this stuff in your Calc 1 course, your instructor wants you to know this, but I'm going to go ahead and tell you right up front, you're going to be able to do this much faster right here in the near future. And there you have it, two examples of using what I call the long way of finding the derivative. We had a linear function here. I went ahead and gave you a shortcut after we did that. The shortcut is if you have a linear function, its derivative is going to be the slope of that line. Whereas when you have a quadratic or any higher order polynomial, yeah, there's going to be a little bit more work to do there. But again, the motivating factor here is this. Very soon, you're going to be able to do these much faster. And that's it for this video. I hope it helped.
Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.